Thursday morning session. It's my pleasure to introduce Oleg Ivrii from Tel Aviv University, who will talk about shapes of trees.
So this is joint work with Peter Lin, Stefan Rohde, and Emmanuel Sygal. So the basic definition is that of a true tree. So a tree T in the plane is called a true tree if the following two conditions hold. So one, we want the harmonic measure of each side of each edge to be the same, as seen from infinity. So what this means is that if you begin Brownian motion at infinity until you hit the tree, there is an equal probability of landing on every edge. And the second condition is that we want the harmonic measures. So for every edge has two sides, and we want the harmonic measures from both sides to be identical. So if we have an interval in this edge, we want the probability that you hit this edge from this side and from this side to be the same. So true trees are naturally related to the concept of Shabbat polynomials. So a Shabbat polynomial is a polynomial which has two critical values, plus minus 1. Given a Shabbat polynomial, you can take the pre-image of the segment minus 1, 1, and this will be a true tree. In fact, every true tree arises in this way. So one has a bijection between true trees and Shabbat polynomials. So, yes. So the fundamental theorem about true trees is that any finite tree in the plane can be conformally balanced. So if we have some tree we can deform it into a conformally balanced tree or a two tree. And this two tree is unique up to RC. So our motivating questions is, how do two trees look like? And what happens when we take the number of edges to infinity? So here I want to mention, I should use this, yes? Theorem of Bishop from 2014. So two trees have been known for quite a while, since Grothendieck, but they have captured the imagination of the complex analysis community since this work of Bishop. And the title of the paper is the main theorem, so it's a very good title. I wish more titles were chosen this way. So what this says is that if you have any compact connected set, then it can be approximated by a sequence of two trees in the Hausdorff topology. So two trees can take any conceivable shape. Okay, before showing you the pictures, let me mention that there's a very natural way to normalize two trees. So given a tree, we'll normalize it so that the Riemann map from the exterior union disk to the exterior of the tree looks like z plus O1 over z as z tends to infinity. This is the hydrodynamic normalization. So we'll normalize two trees in this way. And now it's picture time. Picture time. So we'll have a short break for pictures, and then I'll go back to the slides. It's very dark in here. Time to tell ghost stories. It was a dark and stormy night. Down. So are the definitions clear? Perfect. So can we use the arrows? So the online participants are playing computer games.
We apologize for technical difficulties. It seems the equipment behaves today even worse than previous days.
Okay, how about this? The online participants can follow the slides I sent them. Okay, so if I do this, you'll change the slides. Okay. Okay. So here, so this is a true tree with 9 edges. And this is a random tree with 2,000 edges. And most edges are very, very short. The continuum version was studied by Peter and Stefan in a previous work. And they show that the continuum limit exists. So here in this picture, I have drawn the continuum self-similar tree, its true version, which was studied by Mario Bonk and Hui Tran. In both of those trees, the individual edges shrink to 0, the diameters. The focus of this talk, however, will be the infinite trivalent tree. And it turns out that the individual edges don't shrink to 0 when you add more edges. So when I was at a conference in Mexico, Stefan gave a wonderful talk, and he noticed that, so what are we doing here? To give a conformally balanced shape to the infinite trivalent tree, what we do is we truncate it at level n, take the true form, and take n to infinity. And Stefan Rohde noticed that those pictures seem to converge to the picture of the developed deltoid on the right. But at the time, he couldn't prove it. And one of my main goals of today is to explain this miraculous coincidence. You might wonder what happens when you don't take a balanced truncation of the infinite trivalent tree. So for instance, suppose you start with a tree that has 5 edges, and at each step, you add 2 edges to every boundary vertex. In this case, the trees would again converge. The limit is on the right, but it's a different limit. It's not the developed deltoid. And finally, so I also want to mention that by changing the truncation, you can get any shape you like, giving a new proof of Bishop's theorem. And finally, I have a sequence of trees which converge to the cauliflower, the Julia set of z squared plus 1/4. And in this picture is a bit deceptive because the set of vertices is in one-to-one correspondence with the grand orbit of the critical point of z squared plus 1/4. So that's all my pictures. So let's take this up. Thank you. Sorry? I want to show that the infinite trivalent tree converges to the developed deltoid, which I'll define. Well, if you take the balanced truncations, when you truncate it at level n, you get the developed deltoid. If you take different truncations, you can get any shape you want. So we begin with the deltoid. So the deltoid can be defined in several ways, for instance, in terms of rolling balls. But here, we'll actually look at the conformal mapping to the exterior of the deltoid. And it's just z goes to z minus 1 over 2z squared. So this is the definition we're going to use today. I'll use this board. So the deltoid is what's called a quadrature domain. Which means it satisfies a quadrature identity. But equivalently, it possesses a Schwarz function. So a Schwarz reflection, which is an anti-holomorphic mapping defined on the complement of the deltoid. Which is identity on the boundary. So quadrature domains are a very special and interesting class of domains. Okay. So now we can discuss the developed deltoid. So the Schwarz reflection allows us to reflect the deltoid in its sides. So if we do this, we get 3 new triangles. And if we keep reflecting, forever, the triangles style a domain which we call the developed deltoid, and we'll call it omega. And I believe that in a few years, the developed deltoid will be as much of a household name as Duodis rabbit. So pay attention if you haven't. Thanks to the work of Mukherjee. So now we come to a very important theorem. And this is due to Lyubich, Makarov, and Mukherjee. From 2018. Which says that the developed deltoid realizes the mating of z goes to z bar squared, and the Markov map associated to the group of reflections in an ideal triangle. Well, I'll define it in a second. So the exterior structure it's defined on the exterior unidisk, and it's just the map z goes to z bar squared. And the interior structure so you have the unidisk, and you have an ideal triangle, and if you reflect in its sides, you can tessellate the disk, and the Markov map rho gamma is defined on D minus the root triangle. So it's defined only in these three regions, not in the middle triangle. And it's very, very simple. So on this region, labeled 1, we simply reflect in this geodesic. And in this region, labeled 2, we reflect in this geodesic. And in this region, we reflect in this geodesic. And what's really cool is that those two dynamical systems are compatible. What this means is that, so this is omega, and this is the disk, and we have two conformal mappings from the interior to the interior and from the exterior to the exterior. And so here we have rho gamma, and we can transfer it here in this fashion. And here we have z bar squared. And what this theorem says is that those two mappings agree on the boundary. And if the image, so the image of the root triangle will be the deltoid, and this mating shows its quadrature structure. So let me also mention that Lyubich, Makharov, and Mukherjee show that omega is a John domain, which in particular implies that its partial omega is conformally removable, and hence this is the unique domain which realizes this mating. So now I want to say that those authors, as smart as they are cheaters. And what I mean by this is that they start with the deltoid, a miraculous shape, and they begin to reflect it and use the dynamics of the Schwarz reflection map. So near a cusp, it looks like Z go, it looks kind of parabolic. But instead of having like a 2 or a 3, it has 3 over 2, and it's supposed to be anti-holomorphic. So they use this dynamical nature of the Schwarz reflection to show the genres. And one of our motivating philosophy is to discover the deltoid. So we want to learn about the deltoid and find it. So our strategy proceeds in 2 steps. So the first step is to say that any Hausdorff limit of the Tn's. So Tn is the truncation of the infinite trivalent tree at level n, has the right topological type. So what I mean by this is that it's homeomorphic to the unit circle union the Fari tree. So the Fari tree is the tree dual to this tessellation. And the proof of the step is using moduli estimates. And since we had technical difficulties, I'll just say nothing about this, except that it's, if you believe in the result, the moduli estimates should work. It might take some time because of the parabolic nature of the cusps, but there are no surprises here. So the moduli estimates tell you about the diameters of various species up to some power. So from this, you can deduce that omega is a Holder domain. So the conformal mapping from the disk to omega is Holder. So step 2 is has 2 parts, which are related. So A is to show that any Hausdorff limit realizes this mating. And step B is uniqueness. And this uses something called partial conformal immovability. I'll say more about this later. And we also have a bonus. So if you look at the complement of the developed deltoid, is quasi-convex. I'll erase. So quasi-convex means that, so let's say we have a domain. Well, okay. So for every 2 points, x and y, here, they can be joined by a curve whose length is bounded above by a constant times the Euclidean distance. And this property implies that omega is John, but is stronger. This property is related to W1P removability studied by Koskela and his co-authors. So to prove this, we first show that the complement of the field Julia set of z squared plus 1/4 is quasi-convex, which seems to be a new result. And if you prove this without cheating, then you also get this bonus. But you have to not cheat. You have to not use certain specifics of this Julia set. Are there any questions? Is everything clear? Okay. So let me discuss exterior structure. So let me draw a picture of the developed deltoid. Omega. And we can ask, what is the harmonic measure on the boundary? So we have infinity, and we ask, how does this harmonic measure look like? So here, omega is a subsequential limit of the TNs. So how does the harmonic measure on this look like? And the claim is it is what you expect it to be. So for instance, the harmonic measure of this part of the boundary is 1/3. And the harmonic measure of this is 1/6. And the harmonic measure of this piece is 1/12. So the harmonic measure is what you expect it to be. And to prove this, you look at the finite approximating trees. So you look at the TNs. Now, when n go, so the harmonic measure lives on Tn, but since there are many edges, the harmonic measure of each individual edge tends to 0. And in fact, because those sides close up, if you want to reach a particular edge through by Brownian motion, you have to go through this very narrow gap. So this has small probability. So the harmonic measure of those finite approximations lives on the entire tree, but when you take n to infinity, the harmonic measure would actually live on the boundary. So those, in fact, it's quite easy to see that those harmonic measures converge to this thing over here. And now to study harmonic measure, one just has to count the number of edges, because the definition of two-tree says the probability of hitting every edge is the same. So this arc subtends 1/6 of all the edges in the tree. So this is how you deal with the exterior structure. Okay. To deal with the interior structure, we need the concept of relative harmonic measure. So let's say I have a simply connected domain, U, and arc I on the boundary. I should pick this up. I don't want to step on this. And a point P also on the boundary. And I ask you, what is the harmonic measure of I as viewed from P? And you would say this is a very silly concept. And your reasonable answer would be 0. So if you take P and approximate it by a point Z, you get 0. However, what you can do is talk about the relative harmonic measure of two intervals. So if you have two arcs, I and J, you can talk about the relative harmonic measure, and it's defined as this quotient. So this concept is well defined. So I hope this definition makes sense. Sorry? Well, it's the relative harmonic measure. It's not a measure, it's just a number given to intervals I and J. You define this number in this way by taking the limit. So you take a point Z and you look at the quotient of those two probabilities. Well, if you want to simplify things, just take a Jordan domain. Okay, so this is the picture of a subsequential limit. And if you draw the dual tree, it subdivides omega into complementary regions, which we call omega horoballs. So this tree subdivides omega into domains which we call omega horoballs. And the main theorem is that if you take two edges, say E and F, lying in an omega horoball, so if E and F are two edges. So here we are discussing the limiting picture for a subsequential limit. So the theorem says that they have the same relative harmonic measure. So as viewed from the cusp. And the second statement is that if we have an edge, say E, it belongs to two different omega horoballs. And what it says is that the relative harmonic measures essentially coincide from both sides. So if we have two intervals I and j in this edge, or two arcs, then the relative harmonic measures are the same. Oh, sorry, IJ.
Oleg, we have a question from online audience. So what is, asking to remind, what is an omega horoball?
An omega horoball is the complementary region of omega minus the tree. So the Hausdorff limit of the trees Tn looks like an infinite trivalent tree union partial omega. So the complementary regions are omega horoballs. So the proof of the statement essentially is follows from the fact that Tn is a two tree and the Markov property of Brownian motion. For instance, let's take a look at the first property. So if you look at a finite approximation, well, it looks something like this. Well, how should I draw it? So this is a finite approximation. This is Tn, and you have infinity. And if Brownian motion starting from infinity is supposed to hit either E or F, okay, this is E, this is F, it has to pass through this very short gate. So the fact that Tn is a two tree means that the relative harmonic measures of E and F are approximately the same. So this is a proof of this theorem. What's the upshot? So here we have the disk, and here we have omega. Which is a subsequential limit of the two trees. And here we have the tiling by ideal triangles. And both of those pictures feature dual trees. So the dual tree here is the Fari tree. And the dual tree here is we are interested in. So we call complementary components here Fari horoballs. And it's very easy to see from the symmetry of the Fari horoballs that they satisfy those two crucial properties, because it's a very symmetric picture. So what we can do is we take each Fari horoball and map it conformally to the corresponding omega horoball. And we normalize the conformal mapping so that the cusp goes to the cusp and two vertices go to the corresponding two vertices. And then, of course, the two properties imply that all the vertices line up. So, in fact, more is true. Those two properties imply that the phi i's glue up to a conformal mapping of the disk to omega. And this is the interior structure theorem, and this shows that any subsequential limit realizes the mating. Uniqueness is similar. Yes.
Sorry, yeah, just one question. So what's the difference between omega and, let's say, unidisk? So how do you build omega? So what's the difference? I mean, I was sort of all
so the way
impression that we are basically going to fill up the disk.
So the way omega is created is we have those T ends, those two trees, and we take the limit as n goes to infinity. And we show that they have the same topology. That's one of the statements. So when we take the limit as n goes to infinity of the two trees, we get an infinite tree union a Jordan curve. And omega is the domain bounded by this Jordan curve.
Triangles that you get inside is just sort of connecting the.
Yes.
Okay.
So I draw the triangles to make it easier for me to draw a plausible picture of omega. Okay, so let me say a few words about uniqueness, and this will be the end of my talk. So for uniqueness, well, suppose we have two different subsequential limits. We have two different omegas, omega and omega prime. And both pictures have are decomposed into omega horoballs and omega prime horoballs. So what we can do is we can map each omega horoball to the corresponding omega prime horoball conformally and map the exterior to the exterior. And those two statements essentially explain that all those conformal mappings blew up. So what we have is we have a mapping phi from C minus partial omega to C minus partial omega prime, which is conformal and extends continuously as a mapping from the Riemann sphere to itself. And what we want to do is we want to conclude that phi is Mobius. So one way to do this is to say that partial omega is John, or so omega is John and hence conformally removable, but this is cheating. And the reason this is cheating is because our construction applies not just to the developed deltoid, but we can build a ton of very interesting dynamical systems. We can build Julia sets, we can build quadrature domains like the Talbot curve, and we can build homomorphic correspondences. So there is a result of Pelabekos which says that the Sierpinski-Gasker is not conformally removable. So most natural shapes are not conformally removable. And therefore, we use something called partial conformal removability. So the thing is that our mapping phi is not a random mapping. It's not just any old conformal mapping. The modular estimates show that those two, the geometric structure of the omega horoballs and omega prime horoballs are approximately the same. So it's best to use partial conformal removability. And I'll stop here.
So since we got out over time, we don't have time for long questions, but maybe there are some quick comments, remarks, quick questions from the on-site audience. No, then any questions from online? Okay. Kirill, you can talk.
Oh, okay. I had many questions, but maybe I can ask just one quick one. So in this procedure you have of adding on lots of new edges and seeing what the limit is, do you have a criteria for when the limit kind of closes up? So when the complement of the limit is going to have more than one component, or if it's going to look like these continuum trees that you showed earlier?
So I would say that we have some methods, and the methods are very general, but we look in a case-by-case basis. But any tree which looks like the infinite trivalent tree is going to be, they're going to close up. And this we can state as a kind of theorem.
Any other questions, comments? If not, let's thank Oleg again for the wonderful talk.